Okay, so now that we know how to solve homogeneous equations with constant coefficients, let's take a look at linear non-homogeneous equations. We're only going to consider a few special cases in this class. In any case, before we get started, we need to introduce some terminology. So, definition. Let Ly equal f of x be a linear ODE. The inhomogeneous term of the ODE is the function f of x. I think I might have defined this already, but it's worth recalling. Okay, so if you have a linear operator acting on y, then that'll make the left side of that equation into a linear combination of y and its derivatives. And then if you set that equal to some f of x, then that f of x doesn't have a y or a derivative of y associated or multiplied by it. And so then we call it the inhomogeneous term. So in the past, we've always dealt with homogeneous equations, which is when that inhomogeneous term was just zero. Now let's consider the case that it is something other than zero. So, another definition. Again, let Ly equal f of x be a linear ODE. The associated homogeneous ODE is the equation, well, the differential equation, the ordinary differential equation, Ly equals 0. So the associated homogeneous ODE is when you take the inhomogeneous term and you just pretend it's 0. That's it. Okay. Now this next one has a name that's slightly unfortunate. Lots of books, including ours, calls it the complementary solution. Other sources call it the complementary function, and even that's not quite correct. So I'm going to call it the complementary family. So the complementary family of the ODE is the general solution of the associated homogeneous ODE. Okay, so if I give you a let's just look at an example here. If I give you something like y prime prime plus 6y prime plus 9y equals e to the x. First of all, you should recognize that this is a linear this is a linear non-homogeneous ODE with constant coefficients. You can construct the associated homogeneous ODE by just taking that same ODE and making the inhomogeneous term 0. And then the complementary family is just the solution of the general solution of this ODE right here. And we know how to find that because of the previous 2 lectures. Okay? The reason why I was so hesitant about calling this the complementary solution is because it is a solution of this ODE, but it is not a solution of this ODE. You see the problem, calling it a solution when in fact it's not a solution. So instead we'll just call it the complementary family. So there is a theorem that we need. Theorem. This is called the solution theorem for linear non-homogeneous ODEs. Or stone. Anyway, suppose Ly equals f of x is a linear ODE. Let yc be the complementary family of the ODE. And let yp be any particular solution of the ODE. Any particular solution whatsoever. The general solution of the ODE is y equals yc plus yp. Okay? So, to summarize, you have a linear non-homogeneous ODE with constant coefficients. Actually, it doesn't even have to have constant coefficients, but it will in our class. You have a linear non-homogeneous ODE. If you can find the complementary family, which you can find by just replacing this f of x with a 0 and then solving that, and you can find any particular solution whatsoever of this ODE, then the general solution is just the sum of those two. That's it. Okay, so we already know how to find the complementary family of a linear ODE. We know, with constant coefficients. We know this because of the previous 2 lectures. Okay? What we don't know yet is how do you find a particular solution of this ODE? That's the main thing that we're going to be focused on today. So there's more than one method for figuring out this particular solution. We're going to use, in this class, a method called the method of undetermined coefficients. And the way that works is, well, first of all, it only works for certain functions. Like this has to be a particular function. It has to be an exponential, sine or cosine, or a polynomial, or some sum or product of those things. Okay? In any case, we have a way of dealing with each of those types of functions. So here's how it works. If the inhomogeneous term is, I'll just call it f of x, then make the guess okay, if the inhomogeneous term is e to the kx, for example, well, in that case, what you want to do is you want to come up with, this is a very common procedure in math, you come up with a guess and then refine that guess until you get the right answer. So we'll make the guess yt, I'm going to call it yt, t stands for trial, but ultimately the hope is that it will become yp. This is going to be a times e to the kx. Okay? So before we go any further, we're going to look at some examples of how this works. If my tablet will behave. Okay. So, let's look at the following example. Y prime prime minus 2y prime minus 3y equals e to the 4x. The idea here is that you need to make a guess as to what the particular solution will be, and then refine that guess as you move further into the problem. In this case, let's think about this for a second. We have the second derivative, the first derivative, and the original function in a linear combination equaling an exponential, e to the 4x. So, what happens if you take a similar exponential, perhaps times a constant? Well, let's think about that for a second. If you take a few derivatives of this and you put them in a linear combination and add them all up, what are you going to get? You're going to get a constant times e to the 4x. And so that's exactly what we're having here. So this is the sort of guess that we want to make. Okay? Notice that I am making this guess completely based on the inhomogeneous term. The rest of the equation has nothing to do with the guess that I'm making. Except in the case of duplication, which is something that we'll get to in a future lecture. let's suppose we had something like fourth derivative of y minus 2y prime prime plus y equals cosine of 4x. What do we do now? Well, if the inhomogeneous term is a linear combination of sine and cosine, so something like sine of kx or cosine of kx, then you make the guess that it will be a linear combination of cosine kx and sine kx. Okay? So, in this problem here, our guess should be yt equals a cosine of 4x plus b times the sine of 4x. All right, so suppose you have something like y prime prime minus y prime minus 2y equals like x squared plus 4. Oh, by the way, I should make a comment about this guess right here. The idea is, again, you want to look at the inhomogeneous term, just that, and think about all the derivatives of the inhomogeneous term. All the derivatives of cosine of 4x are going to look like constant times cosine 4x or constant times sine 4x. So if you look at a linear combination of those, then what you're going to get is a linear combination of cosine 4x and sine 4x. And that's exactly what our guess is. Okay? So, back to this next example, we have here a polynomial of degree 2. So what should be our guess? Well, we want to think about if you take derivatives of a polynomial of degree 2, and you take like a linear combination of those, what you're going to get is a polynomial of degree 2 or less. Okay? And so that's exactly what our guess is going to be. So if you have a degree m polynomial, then your guess is going to be another degree m polynomial. We'll call it am x to the m plus am minus 1 x to the m minus 1 plus dot 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 all the way up to a1x plus a0. So, in our case right here, we have a degree 2 polynomial. So the guess is going to be a degree 2 polynomial. ax squared plus bx plus c. Okay. And these are the three basic families of functions that we're going to be working with as the inhomogeneous term. But you can also take products of them. In that case, you just take the product of the guesses. You can take sums of them, in which case you take the sums of the guesses. That's all there is to it. Okay, so let's look at some more examples of how to come up with a guess based on the inhomogeneous term. And I promise we will get to actually doing out a full example in its entirety in just a moment. So let's suppose we have y prime prime plus 5y prime plus 6y equals x plus 1 cubed. Okay, x plus 1 cubed is a degree 3 polynomial. Therefore, our guess should be a degree 3 polynomial. So, the guess that we would make is like ax cubed plus bx squared plus cx plus d. Suppose we had third derivative of y minus 16y prime prime plus 64y prime equals e to the x times cosine x. Okay. Well, that's not an exponential, and it's also not sine or cosine, but it's a product of those two things, right? So the guess that you would make is just going to be the product of those two guesses. We're going to have e to the x times a cosine x plus b sine x. And if you're wondering why this isn't like, let me take a moment to explain something here. So you might be thinking we should have like a e to the x times b cosine x plus c sine x. I said that in the wrong order, but I wrote it correctly. Literally, yes, this is what we ought to do. However, if you just distribute this a through, then you'll get that this is e to the x times ab sine x plus ac cosine x. And now AB is just a constant. AC is just a constant. So what's the point of calling them AB and AC? Why not just call them A and B? And so that's why we can simply just say that this is going to be e to the x times A cosine x plus B sine x. Okay. Suppose you had y prime prime. Actually, I don't want to do that one. Let's say there are plenty of examples in my notes, but I'm just taking a few. 2y prime plus 5y equals x squared e to the x. Well, that right there is a product of a degree 2 polynomial and an exponential. So, our guess is going to be the product of a degree 2 polynomial and an exponential. So, that'll look like ax squared plus bx plus c times e to the x. And again, you might be wondering why we don't have d e to the x. The answer is because we can just distribute the d among these constants, and then those constants can absorb the d. Okay, and let's look at one more. Suppose you had fourth derivative of y minus y equals cosine of 2x minus x? Well, that is a cosine minus a degree 1 polynomial. You could also say it's cosine plus a degree 1 polynomial, where the degree 1 polynomial is negative x. Okay? So what we need to do is take the sum of those two guesses. For cosine of 2x, our guess would be like a cosine of 2x plus b sine of 2x. And then for x, our guess would be like ax plus b, so that'll be cx plus d. Okay? So hopefully at this point we get the idea of how to construct a guess for the particular solution based on what the inhomogeneous term looks like. So, since we're set with that, let's do some examples of actually doing out these equations in their entirety. So, before I erase it, remember, Stone is going to require us to figure out the complementary family and a particular solution. We're going to need both. Okay? So let's look at the following example. The first example in my notes is a little too hard, so I think we're going to start with something easier. Let's say we have y prime prime plus 5y prime plus 6y equals e to the 2x. All right? So, we're going to need two parts. We're going to need the complementary family, which we find by solving the associated homogeneous equation. And we're going to need a particular solution, which we get by finding a guess and then refining that guess as time goes on. So first, let's start with finding the complementary family by considering the associated homogeneous equation. In this case, that's going to be y prime prime plus 5y prime plus 6y equals just 0. That is the associated homogeneous ODE, right? And then we need to solve that. Well, we can solve that based on the previous two lectures. We can turn this into the characteristic equation r squared plus 5r plus 6 equals 0. Factor that into r plus 2, r plus 3 equals 0. And then we have two roots. r1 equals negative 2, and r2 equals negative 3. And then the solutions that those generate are e to the negative 2x and e to the negative 3x. And then y equals c1 e to the negative 2x plus c2 e to the negative 3x is the general solution of our associated homogeneous equation. So in our context here, we'll call that the complementary family, YC. Okay? Okay, now here's the new stuff. The new stuff is we have this inhomogeneous term here, so we're going to have to construct a guess based on the inhomogeneous term. Since it's an exponential, we're going to have the guess be a constant times an exponential. So yt, t stands for trial, is going to be a e to the 2x. The goal from here is to figure out A. Once we've got that, we'll have a path to solving the problem. In some sense, this is a little bit like partial fraction decomposition. In partial fraction decomposition, you wrote this form that had these unknown constants in it, and then you had to find those constants, right? Yeah, that's pretty much the same thing that we're doing here. That's why it's called the method of undetermined coefficients. Okay? In any case, how do you figure out what A is? Well, what you've got to do is you've got to take this trial and plug it into the original ODE and see what happens. So, in order to put this into this ODE, we're going to need two derivatives. So yt prime equals 2a e to the 2x. Then the second derivative, yt prime prime, is 4a e to the 2x. Okay, so then let's put that information back into the original ODE. So we get 4a e to the 2x, that's y prime prime, plus 5 times 2a e to the 2x, that's y prime, plus 6 times a e to the 2x, that's y. This needs to be equal to e to the 2x. So let's see here. This is 4a e to the 2x plus 10a e to the 2x plus 6a e to the 2x equals e to the 2x. From here, you can combine like terms. So we have 20a e to the 2x equals e to the 2x. So then if 20a e to the 2x equals e to the 2x, what do you suppose 20a is going to have to be equal to? You just divide both sides by e to the 2x, you get 20a equals 1, right? So 20a equals 1. In which case a is 1 over 20. And so the particular solution that we were looking for is 1 over 20 e to the 2x. Now then, according to the solution theorem for linear non-homogeneous ODEs, the general solution is just the sum of the complementary family and the particular solution. So c1 e to the negative 2x plus c2 e to the negative 3x plus 1 over 20 e to the 2x. And that is our general solution. Okay? They always go like this. You always solve the associated homogeneous equation, which you do by using the methods that we discussed in the previous two lectures. You come up with the guess. You'll need a few derivatives. You put that into the original ODE, and then figure out what that implies for the constants. And then once you have the particular solution, you just add that to the complementary family, and you're done. Okay. Now let's look at another example. Let's say we want to find the general solution of y prime prime plus 3y prime plus 4y equals 3x plus 2. Okay, so first thing we've got to do is find the associated homogeneous equation, which is when you take the left side and just pretend the right side is 0. Y prime prime plus 3y prime plus 4y equals 0. We need to solve that in order to find the complementary family. Okay, so we look at the characteristic equation. R squared plus 3r plus 4 equals 0. That one has non-real roots. So r equals negative 3 plus or minus the square root of 3 squared minus 4ac divided by 2a. This turns into negative 3 plus or minus the square root of 9 minus 16 is negative 7 over 2. So this is negative 3 halves plus or minus I root 7 over 2. Then, using Euler's formula, we can say this is e to, multiply this all by x. We can say this is e to the negative 3 halves x times cosine of root 7 over 2x plus I sine of root 7 over 2x. And so the complementary family just ends up being e to the negative 3 halves x times c1 cosine of root 7 over 2x plus c2 sine of root 7 over 2x. So that's the solution of the associated homogeneous ODE. Next up, we're going to have to find the particular solution, or a particular solution. Any particular solution would do. The way we do it by undetermined coefficients is we got to come up with a guess first. This is a degree 1 polynomial, so our guess is going to be a degree 1 polynomial. Okay, we'll need a couple of derivatives. So the first derivative is going to be a. The second derivative is going to be 0. You put this information into the original ODE. So you get 0 plus 3 times a plus 4 times ax plus b equals 3x plus 2. All right. In that case, 3a plus 4ax plus 4b equals 3x plus 2. From here, what we're doing is very similar to what we do in partial fractions. We have 4a times x plus 3a plus 4b equals 3x plus 2. Now, we have two polynomials set equal to each other for all values of x, so their coefficients have to be equal. So what we get here is 4a equals 3, and 3a plus 4b equals 2. All right. Well, that makes it pretty clear that a is going to be 3/4. And meanwhile, the second equation becomes 9/4 plus 4b equals 2. Subtract 9/4 from both sides, you get 4b equals negative 1/4. And then in that case, b is negative 1/16. So the particular solution that we were looking for is going to be 3/4 x minus 1/16. And then finally we're done because we just add the complementary family to the particular solution. To get the general solution, e to the negative 3/2 x times c1 cosine of root 7 over 2x plus c2 sine of root 7 over 2x. Add to this 3/4 x minus 1/16, and that is our general solution. Let's do one more example. This one is y prime prime plus 2y prime plus 2y equals the sine of 3x. Again, linear, non-homogeneous ODE with constant coefficients, so we can solve it using the method of undetermined coefficients. So first thing we've got to do is find the associated homogeneous equation, which in this case is y prime prime plus 2y prime plus 2y equals 0. We can solve that using the characteristic equation r squared plus 2r plus 2 equals 0. We can find the value of r by using the quadratic formula, so negative 2 plus or minus the square root of 2 squared minus 4 times 1 times 2 divided by 2 times 1. This turns into negative 2 plus or minus the square root of, let's see, 4 minus 8, so that would be negative 4, divided by 2. So this turns into negative 1 plus or minus I. Okay. As usual, we look at e to the rx. So e to the negative 1 plus I times x. This turns into e to the negative x times e to the ix, which according to Euler's formula is going to be e to the negative x times cosine x plus I times the sine of x. And therefore our complementary family is going to be e to the negative x cosine, I'm missing the constants. We have c1 e to the negative x cosine x plus c2 e to the negative x sine x. Okay. Now let's consider the guess. Yt is going to be a linear combination of cosine of 3x and sine of 3x. All right, we're going to need a couple of derivatives. So yt prime is going to be negative 3a sine of 3x plus 3b cosine of 3x. And y prime prime is going to be negative 9a cosine of 3x minus 9b sine of 3x. You put this all together on the left side, and I'm going to write this in more than one line because writing it in one line would be impossible with the amount of space that I have. So let's see, we have negative 9a cosine of 3x minus 9b sine of 3x. Add to this 2 times the second derivative, which is 3b cosine of 3x minus 3a sine of 3x. Add to that 2 times the original. So that's going to be a cosine of 3x plus b sine of 3x. And all of this added together should equal the sine of 3x. You can combine some like terms here. We have, let's see here, the coefficient of cosine is going to be negative 9a plus 2a, that makes negative 7a. And then 2 times 3b is 6b. So that's multiplied by cosine of 3x. Then on the other hand, we have negative 9b plus 2b, that makes negative 7b. Then minus 6a sine of 3x. This should be equal to the sine of 3x. And what do you do from there? Well, here's how it works. We have here negative 7a plus 6b cosine of 3x plus negative 7b minus 6a sine of 3x equals 0 times cosine of 3x plus 1 times the sine of 3x. Now, cosine of 3x and sine of 3x are linearly independent functions. So that means that if you have a linear combination set equal to each other, two linear combinations of sine of 3x and cosine of 3x set equal to each other, then the coefficients will be equal. What that means in our case is that negative 7a plus 6b is going to be 0, and 7b minus 6a is going to be 1. Okay. So first of all, that first equation implies that 6b is going to be 7a, and therefore b is going to be 7 over 6 times a. The second equation now looks like 49 over 6 times a, minus 6a, which by the way is 36 over 6a. This equals 1. 49 minus 36 is 13. So we have here 13 over 6a equals 1. Therefore, a equals 6 over 13. On the other hand, b equals 7/6 of a. So therefore, b is going to be 7 over 13. Okay. And so from here, our general solution, or well, first of all, the particular solution is going to be 6 over 13 times cosine of 3x plus 7 over 13 times sine of 3x. We add these together to get the general solution, which is c1 e to the negative x cosine x plus c2 e to the negative x sine x plus 6 over 13 cosine of 3x plus 7 over 13 sine of 3x. And that is our general solution. Now, there is a situation in which our guess will not work. I mentioned it earlier. It's called duplication. So that'll be the topic of the next lecture. In any case, I will see you in the next one.